Hello, this is our Gears project and we are Team 53. So to begin, communities suffering from natural and man-made disasters are often in need of immediate aid. It can be challenging to get supplies to these people as the disasters often lead to damaged roads and reduce the capabilities of traditional supply delivery methods. This project aims to fix the problem by having teams design a robot that could potentially autonomously navigate a disaster area and deliver emergency supplies to those in need. To model this situation, the robot was required to navigate through a maze while identifying and avoiding hazards, creating a map, and appearing non threatening in communicating with recipients. Some notable requirements and target goals that we came up with are noted in this table. To fulfill the precise navigation, the target was to have the robot explore 50% of the entire maze. To securely transport the cargo, we had a goal of the cargo container being able to withstand a 25-centimeter drop. For creating the map, the target was to accurately return a map 100% of the time. To avoid damage from hazards, the goal was for the robot to come no closer than 7 centimeters to a hazard. And to be non-threatening, the target was for less than 2.5% of people to find the robot threatening. And lastly, to adequately indicate cargo contents, the goal was for 95% of people to be able to identify the cargo contents based on the labels. To manage our time and workload, we created a Gantt chart with specific tasks and goal completion dates, which can be seen in this picture. One thing to note is that we did get a bit behind on this timeline due to some hardware and software and coding issues that will be discussed later. We worked together on all aspects of the project to ensure cohesiveness and for all the members to have a good understanding of the project.
Design philosophy for building. When designing our gears, our team started by making an engineering specifications chart to keep track of everything the robot needed to do. Our customer needs were that the robot needed to be autonomous, able to navigate, keep cargo secure, create a map of its path, avoid hazards, deposit cargo, appear non-threatening, and indicate the contents of the cargo. With these in mind, we began to brainstorm possible designs for our robot. We came up with multiple ideas for the base, cargo holder, and balance of the robot. For the base, we used the decision matrix shown below to decide what contacts the robot would have with the ground. Through research and testing, we gave each option a rating 1 through 5, 5 being the best, on its ability to meet the customer needs. The decision matrix resulted in the team deciding to make the robot have 2 wheels, a swivel wheel, and a sled to function as best as possible. We also made a functional block diagram that shows all of the components of the robot and how they act with other aspects of the robot. The team also had to design a container for cargo. Through similar decision-making processes, we came to the decision of making a box with a sliding lid. This option was best at holding its lid in place. Our final design is shown here. The swivel wheel is located at the back of the robot under the area for holding the cargo. The main wheels are under the pie toward the center. The sled is at the very front of the robot to keep it balanced. All of the sensors are on the front of the robot. We use 3 ultrasonic sensors pointing left, right, and forward, an IMU sensor to sense magnets, and an IR sensor to detect heat sources. Our cargo container has its sliding lid with designs on it. The smiley face on top helps the robot and cargo look non-threatening. The arrow is to make sure people know how to operate our container. On the front is a logo for what is inside the container. We have logos for food and water, medical supplies, emergency shelter, and fuel that can be easily switched.
For the programming of our robot, we wanted to make sure that it would successfully be able to navigate through the maze regardless of where the entrance and the exit of the maze were. So what we decided to do was to follow the right side wall, assuming that there were not multiple exit points in the maze. So this would allow us to follow the right wall. Whenever there is a right path available, we'll take that, even if there's a forward or left path. And when we get to the exit of the maze, one of the first things shown in the flowchart right before start is if all paths are greater than 120 centimeters, that means all paths are a wide open area, it's outside of the maze, and it will end the program. But if it's not, it will choose the right path, turn 90 degrees, and then drive straight through that portion. And when we're driving straight between grid points, because the maze is on a set of grid points that are an equal distance apart, we will drive forward a shorter distance than the entire distance to make sure that we are successfully able to avoid the hazards. So in this case, if there are no hazards and the current distance is less than 40 centimeters, which is that grid space, we will drive forward 5 centimeters, add that to the current distance, and then again, check if there are no hazards. If there are hazards, or if we're at the 40 centimeters, we will detect the hazard. If there is a hazard, we need to drive backwards to avoid it and turn around and then continue running the main code. But if there are no hazards, we will record the position and record the hazard and then return again until we get to the end of the maze. And as we're storing this map data and we get to the end of the code, we need to output that map data into a reader-friendly format, which is not shown here because we had a lot of problems with the ultrasonic sensors and trying to troubleshoot that, which is the main reason that we were not able to finish all the objectives of this project. We went into office hours many times trying to fix that to no avail. But apart from that, the logic of our code is pretty solid and should be capable of running through the entire maze reliably. There are some negative attributes of our design right now. For example, it is unable to detect heat sources because as we were testing the ultrasonic sensors, we ran into issues and we were not able to overcome those in time to work on other aspects of the code because navigating through the maze required the ultrasonic sensors. So even if we were able to detect heat sources, it wouldn't have mattered unless we got the ultrasonic sensors working. So that's why we chose to focus on that first. There are also problems with following the right side of the map or the right wall. For example, if the exit is directly to the left of the entrance of the maze, it will be a lot less efficient to follow the right path. So potentially adding in a user input to decide if it follows the right or left path might make the navigation a lot more efficient. And currently, our design is not able to actually unload cargo autonomously. It requires user input to come take the cargo and put the cargo container back on once it's emptied. And our solution to this is adding a ramp and basically pushing the cargo container off the side so that it lands upright and is able to be unloaded by humans who need it.
The positive attributes of a robot are that it has a small turning radius, it has the ability to detect magnetic hazards, and it has the ability to navigate the maze. So the way our wheelbase is designed is that the two big wheels have a center of rotation at the green dot, which is the center of mass of the robot. So when it goes to turn, it turns in place and has a 0 meter turning radius. And evidence of this is at the POC. When we tested this, we passed the test and the robot spun completely in place. For the ability to detect magnetic hazards, the robot is able to detect it, and once it senses a magnet, it moves backward and turns around to avoid the hazard. During the demonstration, we started the robot at one of the center checkpoints, and it went towards the magnet, sensed it, turned around and went backwards to avoid it, and then mapped it. And during testing, when we were testing the IMU sensor, it had a 90% success rate of sensing a magnet that was in front of it. And then for the ability to navigate the maze, the robot follows the right wall all the way through the maze, guaranteeing that it eventually will reach the end. And during the demonstration, our robot was able to go forward and go around a corner, showing that it can follow the right wall through the whole maze.
The demonstration of the Gears robot went better than the team was expecting. On the day of the final demonstration, the software for the Gears would not run. The issue was quite complex, and error was occurring in functions defined outside of the scope of the files accessible by our group. This was a huge issue. Our IMU and other sensors could not run without the function, and we were not able to fix it. The final solution to this issue was to revert to an older version of software which contained a different error that we knew. This error would cause the ultrasonic sensors to read an integer that was not subscriptable, subsequently breaking the ultrasonic sensor for the duration of the program. This error was, however, not instantaneous. It would occur at some point between the time the code would run and roughly a minute, although it was normally closer to the 5-second range. These were issues that the group had been trying to tackle for quite some time, but were never able to fix. During the actual demonstration, the robot would run until it reached the end of the maze or this fatal error was reached, rendering its navigation sensors useless. At this point, the map of the maze and table of hazards would be generated. With this limitation in mind, the robot was a success on the small scale. If the robot completely traversed a grid space, it effectively would map that grid space. These two pictures show a story of many of our trial runs being completed. The picture on the left shows the robot in its starting position, while the picture on the right shows the robot in its position after the fatal error was reached and the program was terminated. As one can see, the robot only traversed a fraction of a grid space before the error was reached. In the Gears robot's peak trial, however, nearly 4 grid spaces were traversed before the error was reached. Extrapolating this data, the team believes that if the error was never reached, the robot could have made it out of the maze and mapped its entirety. The robot was also positioned in front of the magnet to test if the program could conduct hazard detection and mapping. This was a complete success. The robot was able to effectively detect, map, and maneuver around the hazard. There were, however, some limitations. One of these limitations was the infrared hazard detection. The code for detecting infrared hazards was never implemented because the hardware and software began to have errors that prevented the entirety of the code from running, and therefore the infrared sensor could never be tested. As mentioned before, it was not until the day of the presentation that the software was reverted to an older version that at least somewhat ran. And by this time it was too late to effectively test the infrared sensor and its part in the program. Another limitation was the robot's inability to detect if it was moving in the correct direction. This means that as long as the robot was angled correctly, drove straight, and always turned exactly 90 degrees, it would never hit a wall. These are obviously all options that could go wrong. Although this issue is only noticeable when it happened, it was only noticeable once when it happened in the demonstration, it could have become more of an issue if the robot were to traverse more grid spaces. With these issues in mind, there are multiple ways that this Gears robot could be improved. The first change would be to work with a whole new set of hardware. As it was mentioned, the errors rooted somewhere in the software or hardware were detrimental to the execution of the code. Many hours were spent attempting to figure out how to fix these errors, but no solutions were ever found. This amount of time spent is why a whole new set of hardware is believed to be our best solution. The next obvious change would be the addition of infrared hazard detection. All that is needed for this to happen would be for the code to simply work for long enough that the feature could be tested. Another change would be the addition of software that could check the correct path of the robot so it's always moving either purely horizontally or purely vertically. This software would most likely make use of the IMU sensor for its gyroscopic features. Although this method could not account for the user error of aligning the robot correctly, it could remove the error associated with driving and turning. The need of this feature is again not entirely known, as the current code prevented the robot from making it far enough for this to come into play. Finally, the addition of a true cargo dropping system accompanied with a message of delivery can improve effectiveness in a real-life situation. With all these features included, the Gears robot could most likely complete another demonstration nearly perfectly. Thank you.